Activity number 1 is a solenoidal inductor. A solenoid is just a coil. Usually you have the loops of wire sort of laying next to each other so they all have the same radius, and it's got a circular cross section, and the cross section is constant. So it looks literally like the circuit symbol for an inductor. Now in this situation, we have a tightly wound solenoid, and it has radius A, it has length D, and it has N turns. So let me draw another picture, but first I'm going to tell you what tightly wound means. Tightly wound means two things. One of them is the magnitude of the magnetic flux density B inside is constant. And B is directed along the axis of the solenoid, like that. And the second thing that we have to say, due to it being tightly wound, is that the magnetic flux density outside is much less than the magnetic flux density inside. These things are true in general if the loops of wire are close to each other, and the length D of the coil is much larger than its radius A. So the length is greater than the radius by a lot. So let me draw another solenoid for us to work with here. I'm going to use my fancy pen. Here I have some loops of wire. I am specifically not drawing them especially close together because I want to be able to draw on this diagram. So here you go. An example of a solenoid. And like we said before, it has length D and it has radius A. And this one is carrying a current I also. I'm going to define a coordinate system here while we're at it. So I'm going to center this solenoid on the z-axis. So that's the z-axis. And I'm going to say we're in cylindrical coordinates, but that's my xy plane regardless. Now, the first question in this activity is use Ampere's law to find the magnetic field inside this solenoid. So 1, find B. How do we do this? Well, we use Ampere's law. The first step to using Ampere's law is how do we choose a contour? What do we expect the magnetic field to look like? Let's look at the picture again. Now, if you remember in class on Tuesday, I said that in general, the magnetic field tends to circulate around a current carrying wire in a right-hand rule-like direction. So if I were to grab this wire right here I would discover that the magnetic field due to that current is circulating around the wire like that. Now I'm assuming that this piece of wire that I'm grabbing is closer to us and this piece of wire is farther away. That's far, that's near, if you're looking at this in 3D. So when I grab this wire, my thumb is going to point this way. My fingers are going to point up on the inside of the coil and down on the outside of the coil. That means that I expect my magnetic field to be positive Z directed inside the coil. And to figure that out, I just used the grab the wire trick. Don't grab the wire in real life, but imagine grabbing the wire and think about what direction your fingers are pointing. Make sure that when you're imagining yourself grabbing the wire, you're using your right hand. Otherwise, you'll get the wrong direction for the magnetic field. All right, so we got that the magnetic field is plus Z directed. We got that it is constant inside the coil. All right, I got to scroll some, so that means I need to redraw the coil. These coils are going to get worse and worse as we move on. Apologies in advance. Now, I also said that because this coil is tightly wound, we have that the magnitude of the magnetic field is small. Let's say it's approximately 0 outside. And we're going to use, I'm going to move that fact. Whoops. We're going to use another important property. So we're going to say that B, magnitude B, is very small outside. And we also said that it's constant inside. So what I'm going to do is I'm going to define an Amperian contour that is directed along the direction of B. So it's going to be positive Z directed inside the coil. There's going to be a rectangle, so it's going to go out this way. And it's actually going to extend all the way out to infinity. And then once I get to infinity, which obviously you never get to, but you know, assume we did, then we do this side. So here's the thing. My Amperian contour has a large contribution from this side. Approximately nothing from this side. Approximately nothing from this side. This thing is trying to autocorrect my drawings, which is not great. And actually nothing from this side. So the only contribution I really care about is the one from the inside of the solenoid. All right, so let's look at that part. So here's where we start using Ampere's law. If you remember, Ampere's law is that mu times the amount of current flowing through some surface S is equal to the contour integral of B around the boundary of that surface. So here's what we do. Looking at our surface again, we have a current that's flowing through the surface as many times as there are loops. So the total current flux through that surface is just going to be N times I, the current that the coil is carrying. Then, how do we find the contour integral of the magnetic field around here? Well, we said that it's constant within the coil. And it's 0 approximately outside. So that means that this is really just the integral from Z equals 0 to the length of the coil, which we named D, of the magnitude of B dz, because dl is z hat dz here. Okay, so what we end up with here is that Ni is equal to magnitude of B times D, the length of the coil. So our magnetic flux density inside the coil is equal to Z hat Ni over D. Only inside. Outside, it's approximately 0. Part 2, how do we find the magnetic flux linkage? So that was the answer to part 1. Part 2, how do we find the magnetic flux linkage? Wow, that's a terrible capital lambda, but okay, there we go. It's going to be N, the number of loops, times the magnetic flux through one of the loops, which in this case is going to be, imagine looking down at the solenoid from above. Here's a loop. That's the area we're talking about. Our magnetic field is coming up from the bottom through this loop, like that. So that would make it N times the integral of B dot ds over a region that is just a circle of radius A. And since B is constant over this area, the flux is pi A squared times magnitude B, and the flux linkage is equal to N pi A squared magnitude B, which means, substituting in the value that we got for B up here, that the flux is N pi A squared I over D, and the flux linkage is N squared pi A squared I over D. So that checks off question 2 out of this example. Question 3 out of this example is find the inductance. Remember that the inductance is just magnetic flux linkage divided by current. So looking at this one and dividing by I, we get that the inductance of this coil is N squared pi A squared over D. Oh, I dropped a factor of mu way back here. Let's go back and put it back in. See this mu? This one right here? I forgot that mu. That mu lives here. That should be Ni mu. So mu Ni over here, mu Ni over there. And that means that there should be a mu over here, and a mu over here, and a mu there. Okay, problem solved. The inductance of the solenoid is N squared pi A squared mu over D, as it should be. Not too bad. And what's the magnetic energy stored in the solenoid if the current is I? That magnetic stored energy is still 1/2 L I squared. So in this case, that'll make it N squared pi A squared mu I squared over 2D. And that is the solution to that problem. Now, activity 2 is for you to do. And this is where I want you to pause your video and do it. Take a look at your handout. But what you're asked to do is design a 100 turn solenoidal inductor with the inductance equals 0.1 microhenries. So you need to choose the length and the radius of this solenoid. Then I ask you to find the magnetic flux density inside. Then I ask you to find the flux linkage inside. Then I want you to verify that the inductance is actually the value that you designed it to be. So, pause your videos, go do that problem, and come back and we'll review, we'll sort of discuss what the answers are. You're all going to get different answers because you might choose different values of D and A. That's okay. It's got a built-in check right here.